What do you get if you add 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, so on? What is 1 plus 0.5 plus 0.25 plus 0.125 plus 0.125 divided by 2 plus 0.125 divided by 4. Yes, I'm getting lazy here. And if we do this for all of eternity, what does that equal? You guys know, you can do this, right? 2. Is that 2? Do you agree with me? Okay, it is, right? Because we're starting at 1, and then we're going halfway to 2, and then we're going halfway to 2 again, we're going halfway to 2 again, and eventually we're going to get darn close to 2. And after all eternity, we're going to be so close that it doesn't matter anymore. We'll underwhelm the precision of any possible machine, therefore, for all intents and purposes, it is 2. You agree this is 2, right? Okay. What do you get if you, well, can you see that this, if we say gamma is equal to 0.5, then this is gamma to the 0 plus gamma to the 1 plus gamma squared plus gamma to the 3rd power plus gamma to the 4th power plus gamma to the 5th power, dot, dot, dot. Do you see that? Because 0.5 to the 0th power is what? 1. 0.5 to the 2nd power is 0.25, so on and so forth. Okay. Turns out we can derive a general equation from this, which looks kind of like this. Sum is equal to 1 divided by 1 minus gamma. And let's see if that works in general. So if gamma is 0.5, this denominator is 0.5. So the whole thing comes out to 2. So that's correct, right? What if gamma is, say, 0.333? 1 over 1 minus 0.333 is 1.5, right? So let's see if that works. If we say 0.333, that's too much of a pain. Let's do a small one. 1 over 1 minus, give me a value for gamma that's simple.
25.
Let's go with 0.2, just because that's easy. All right, it comes out to 1.25. So what if I take 0.2 to the 0 plus 0.2 to the 1 plus 0.2 to the 2 plus 0.2 to the 3 plus 0.2 to the 4 plus 0.2 to the 5 plus 0.2 to the 6 plus 0.2 to the 7. Is that good enough? I think 7 is pretty close to infinity, don't you think? I mean, we're just about there. We're only infinity minus 7 away. So 1.249968. Do you believe if we kept going that would converge to 1.25? Okay. Well, that's as much as I'm going to prove it, but suffice it to say, we've sort of empirically validated that this equation, 1 over 1 minus gamma, is what they'll converge to given enough time, right? What does this have to do with Q-learning? Can you see anything in that? So let's suppose you were to reward this thing. Let's suppose you gave it a constant reward, or let's suppose that your agent succeeded at balancing the pendulum such that it was almost perfectly upright at all times. So it was bringing in a constant reward of 1, best you can bring in, right? Well, if it's getting a reward of 1 at every single time step, what's the Q value going to be? Depends on your gamma value. Let's suppose you use 0.97 for gamma. So it's going to turn out to be 1 over 1 minus 0.97, which is 1 over 0.03, which is 33.333. So I'm going to claim your Q values will converge all the way up to 33.333 if you have a gamma value of 0.97 and you give it a constant reward of 1. You see where I get that from? Okay, so let's suppose your neural network is capable of outputting values from -1 to 1, which, by the way, it is. Do you see a problem? Well, there's a problem because those Q values, or those rewards, are going to accumulate, and they're going to accumulate to something close to that, and your neural network won't be able to represent it. And so what's going to end up happening is it's going to start saying, hey, if I go this way, I get a reward of 29, and if I go this way, I get a reward of 33. And as far as it can tell, it's going to see 1 no matter what it does. And it's going to learn that it doesn't matter what it does. Doesn't matter what it does. Well, some things are better than others. So basically, we have more than saturated our neural network, even though we've only given it rewards of 1, because our gamma value was 0.97. So you actually do have to play a little bit of games. Maybe you could make your reward be 0.1 instead of 1, and then it'll converge to 3.333, which is still too much, but yeah.
Will it make any change if I change my final neural net to linear layer instead of hyperbolic tangent?
That's a good question. Yes, that's a technique you can use. So let me be specific just to make sure everyone knows what we're talking about. Temp, let's see, I'll do the Java one today because I did the C++ one last time. If we look at main.java, here we're making a neural network. And you see our neural network has a linear layer followed by a tanh layer, followed by a linear layer, followed by a tanh layer, linear layer, followed by a tanh layer. The whole reason your neural network can only handle values between -1 and 1 is this tanh layer. If we go to some plotting function, and we say plot tanh of x, this is a plot of the hyperbolic tangent function. And as you can see, it has a range from -1 to 1. And because of that, because this last layer in the neural network is a tanh layer, that means every value that goes through it is going to come out squashed into that range from -1 to 1. So the question is, what if we just do that? We make our neural network have the last layer be this linear layer instead of this tanh layer. Will that work? The answer is yes, it does work. The only risk is it makes it slightly more unstable. So in order to train a neural network like this, you need to make your learning rate much, much smaller. Whereas right here, I told you to use 0.03. If I were using a linear output layer, I'd switch to something like 0.003, something a lot smaller, because these linear output layers tend to kind of explode the gradient in funky ways. But as long as you use a small enough learning rate, that does work. And that also gives your neural network the ability to handle arbitrarily large output values. There's one other reason I don't like to do that. While becoming more unstable, it also takes longer to train for two reasons. One is I have a much smaller learning rate now, which means it's going to take longer to train. And the other one is it still has to reach out there all the way up to 33 when it's used to getting smaller values. So it takes a lot of steps for it to train to get all the way out to that range. Does that make sense? So if we just use a tanh output layer and a reasonably large learning rate and normalize the values, it tends to learn a lot faster. Therefore, I usually recommend we just normalize our values. It takes care of the problem more elegantly. But that's good thinking. That actually is a reasonable solution. So, yeah, one of the reasons some of you might have models that are not converging could be this. I didn't quite teach that very well yet, but hey, at least I'm doing it now, hours before this thing is due. Maybe you'll be able to pull it off. So one of the solutions that was suggested is if we use a smaller value for gamma, right? If we make gamma smaller, like 0.8, then what's this value going to work out to be? 1 over 1 minus 0.8 is equal to 1 over 0.2 is equal to 5, right? which now if we use a reward that goes all the way up to say 0.2, which is the reward you ended up using, okay, well then this is going to max out. If the reward is 0.2, 0.2 over 1 minus 0.2 is going to work out to be 1. And so the maximum value that all these Q values will ever accumulate to will happen to be 1. And the neural network can represent that. And so we won't saturate it with unrepresentable values. And there you go. If the value is greater than the neural network is capable of representing, it will be clipped. Right? If you tell, for example, if your x value is right, if you're right here where that hand is, and I say, okay, shift that x value such that your output value is 7, what's it going to do? It's going to move this way by the step amount, but it's never going to go so far that it becomes 7, because no matter how far it goes, it's still only going to become 1. And eventually it's just going to say, I can't do it. So that's what the neural network does. I felt like I missed the question though. So the inputs, if the inputs are not in the range of -1 to 1, it will eventually adapt. If the outputs are not in the range of -1 to 1, and we use a tanh output layer, there's nothing it can do. It cannot adapt. It'll just saturate at 1 and poop out. So you manually hacked your Q-table values to kind of keep it in the range you wanted?
Yeah.
Okay, cool. By the way, experiment away. I really like that you guys are messing with it, because that's really the greatest way to learn. I do hope that by the end of this class, you'll be able to do all the math and figure out how you'd get it to saturate exactly at 1 if you wanted it to. But yeah, if you didn't know that right away, that's totally understandable. I haven't entirely taught it yet. But yeah, that is a thing. I hope one of the ways you would have debugged this is you would have, if you had this problem, for example, I hope you would have started looking at the decisions it's making, and you would have seen that, oh, hey, it's trying to choose between a value of 1, a value of 1, a value of 1, and a value of 1. And it can't tell which one's better because they're all 1. And then you would have known, hey, my values are all going to 1. What's up with that? I haven't seen anybody asking questions like, well, what do I do when my values all converge to 1? But let's see, how could you debug from that point? I guess you'd have to somehow know the reason it can't get past 1 is because the neural net saturates at 1. I did mention that, but I'm not sure you would have thought of it. And if you understand this math, you can see how those rewards accumulate, and that explains it a little better. Okay, is it clear kind of what's happening there? Okay. Yeah, so Q-learning is not some standard, the only right way to learn or anything like that. It's somebody's way of understanding the world and some way of hacking it together. And we've talked a little about how Bellman made this equation, but that doesn't mean that that's the only true model of the universe. This is just one thing we can do. So anything you do that works, if it works, hey, it's valid. If it doesn't always work, then maybe it's not as valid. So one thing data science is really big on is empirical validation. If it works, everybody's happy with it. Yeah.
I haven't tried this yet, but is it valid that the gamma value more than 1?
So let's talk about what gamma would do exactly. I'm going to come back to our simple grid world for now because I think it's easy to reason in a simple grid world. Now, let's suppose you're going to start right here. And let's suppose you're trying to get to that donut. I picked a donut because it's really fast and easy for me to draw. If the reward for getting to the donut is, say, 100, then basically, let's suppose your gamma is 0.99. Do you see that then the value of being in, say, this state is 0.99? And the value of this state is 0.99. And the value of this state is 0.99 squared. I'm assuming you can do the 4 actions left, right, up, and down, right? Okay. Let's suppose now gamma is equal to 0.01. Now the value of being here is 0.01. And the value of being here is pretty much nothing, right? And the value of here is 0.00001, something like that, right? Well, let's suppose there's another donut. We'll say a small donut right here. And the reward for getting that donut, I'll add some more states to our game. The reward for getting that donut is 2. Which should you go for? The big donut? The big tasty donut with sprinkles and maple syrup and gummy bears stuck on it with Oreo crumbs and a strip of bacon. Okay, so the ultimate donut, and this is a Cheerio. Okay, should you go for the awesome donut or the Cheerio?